Let's continue. Okay. There is a lot of different cases, and we're just adding one more case after another case. So every time at the beginning, we basically review a little bit of what we have so far. Basically, we have this one, and we try to solve the eigenvalue and eigenvector. Let's just say lambda and v. Okay, for this matrix. Somehow nothing tells us the information about the solution of the differential equation. Now, so far, if we have a 2 by 2, we have the first case is all the eigenvalues are real. They can be both positive, both negative, or one positive, one negative, corresponding to source, sink, and part source, part sink, which give you a saddle. Okay. The second possibility is you have something which is called a complex. Pretty common. Okay. Once you have something complex, basically you are going to have in your phase plane a spiral. Okay. Well, you have two choices. The first one is spiral in, which means you're actually gradually reducing to 0, 0. That gives you a sink. Similarly, you have a spiral source. That means you rotate. Meanwhile, you get bigger. Okay, so you're going further and further away from 0, 0. In that way, you have a source. Of course, as you rotate, if you don't get bigger or get smaller, you stay constant, you will have something called the center. Okay, that will be the first case. The key is take A plus BI and look at this A. Okay, the real part. The imaginary part only takes care of the rotation, and it really doesn't change the size of the solution at all. Finally, we are two more cases. The first one is called degenerate. Okay. Basically, what we have is we have a two-dimensional system. Let's just don't do this. Just do this. But then turns out the whole thing looks like a one-dimensional system. And keep going. So you don't see any rotation or any kind of trend going in two-dimensional behavior. You only have one dimension. Every single behavior is parallel to each other. If you're in this direction, once you have a point, you just never move. You don't move this, you don't move like that. Therefore, only can move left and right based on this. That's called degenerate. And we did the calculation. It's really no big deal. It's pretty easy to calculate. Just pretend 0 is another eigenvalue. So the only thing left is repeated real. After that, we're all done. So let's look at this one. Where A equals -2, -2. Okay, quick calculation. So technically we have two solutions and both of them are the same. So we have a multiplicity of 2. Okay, -2 repeat for twice. Well, what trouble does it make? Well, you can still do the eigenvector. So your eigenvalue is going to be 1, 0. The eigenvector. Then the first solution is going to be e to the -2t. Okay. Now you see the problem. right? If we have two real, we have another eigenvalue with another eigenvector, we will have all we needed. We need two linearly independent solution, right? But for this case, however, we don't have it. We have -2, we have 1, 0, and we don't have the other one, unless you want to put it again. And if you do the same eigenvalue, you will have the same eigenvector again. So really, you just repeat the same thing for twice. Clearly, they are not linearly independent anymore. They're basically the same vector with the same solution. Sounds good? Okay, so here's our job. We want another one. Where is this missing eigenvector? And what is the corresponding solution? That's what we're looking for. Sounds good? All right, let's go ahead and find it. We failed this, but we haven't failed the original thing. That is, this one technically can be written as, okay, let me do it. This can be replaced by x prime, y prime. Linear system is nice, but even without linear system, it's just this. Okay. Let's solve it the old-fashioned way. From the bottom, put it into 1. Okay. Take a closer look. This is doable. Okay. Numerical integrator, you can verify by yourself. It's pretty easy to figure out. Which give you this. Which is our integrator. Integrated factor, actually. Okay. After that, this equals C. Okay. CT plus D. X equals CT. Okay. Now check. We need two solutions, right? Definitely from here, we got e to the -2t, e to the -2t here. So far, so good. By doing all the math, we did find another solution which looks like this. It's basically e to the -2t multiplied by another t. Okay. So go back to the solution. This is what we got. We were saying we are missing another one. Now we did find another one, even though through the original method, by doing everything separately, we do have another one, which look like these. We still don't know what this vector yet. Okay, we still don't know what it is yet, but we did find a solution, which seems like it will work. Make sense so far? All right, so this is what we have so far. If lambda equals -2 for twice, we do have this one, but now we have additional one, which is t times this one. Okay, then the final solution should look like this. Both of them come from the same eigenvalue, so you have -2 again, but by adding a t, they become linearly independent again. So you do have these two. Now our job is try to give a formula for this vector here. Sounds good? Now let's go ahead and try to find a vector. Well, you already know y prime equals ay. Moreover, y equals this. I'm just going to use lambda in general. Okay, in this case, lambda equal to you want to find v0 and v1. We can just plug them in. Here, we use the product rule to calculate the derivative. Okay, let's clean things a little bit. Hold on. Let me make sure I'm doing the right thing. Lambda v1 k2 forget about the k. We can absorb the k back into the eigenvector, so let's absorb the k to save some trouble. Okay, now it looks nice. This lambda v0 plus e lambda plus v1 plus t e lambda t lambda v1. Okay. That's your y prime. Here. Now let's calculate ay. which is e to the lambda t AV0 plus t e to the lambda t AV1. That's from your AY. Let's pause a little bit. Make sure you're okay with the calculation. Okay, do everything. Put all the e to the lambda t together, and put all the t times e to the lambda t together. Looks okay? All right. If that is okay, these two are supposed to be the same because y is a solution, right? That means these two have to be the same. If these two become the same, remember they come from different terms. One is e to the lambda t. The other one is t times e to the lambda t. That must mean the corresponding thing has to be the same. Okay? Then you have two possible cases. Number one, look at these two. Case one, lambda v1 equals AV1. Okay. Case two, v1 equals 0. Then check this part for the e to the lambda t. Lambda v0 plus v1 equals AV0, which implies lambda v0 minus AV0 minus lambda v0 equals v1, which implies a minus lambda I v0 equals v1. All right. Is everything making sense? A lot of calculation. You can follow after you receive the notes. It's really not difficult. Okay. But what we end up with, if we summarize, We want our solution look like this. V0 plus t e lambda t v1. Now we do have a way to find v1 and v0. v1 equals this, which means v1 is actually the eigenvector of lambda. Once you have v1, you solve v0 from here. In this way, you'll find v1 first. Then you solve for v0 next using this. This will be the solution of repeated eigenvalue. Okay, let's finish. We start from this one. We found lambda equal to -2 for twice with the eigenvector 1, 0. Okay, then we write down the solution. We find it's not doable. Now we know how to do it. We know the answer is this. Moreover, v1 satisfies this. That means v1 should be this vector here. But what about v0? Well, we just need to set up a minus lambda I, which means a minus lambda I and your lambda, you know, it's -2. V0 is AB. Which come from V1 here. Okay. Therefore, B0 equals 1, 0. B equals 1. Oh, that's degenerating. I see now. Okay. So V0 equals 1. This can be anything. Doesn't make sense, does it? A minus lambda I. So I still cannot do it. I have to do the initial value. Too bad. B is 1. It's K1. This is K1. Now it's K2. Okay. If I add this, what will happen? That would work. All right. Let me clean things up a little bit. Let's clarify several things. Okay. Number one, all the calculation is here. It's correct. Number two, we did several modifications. K2. Okay, let me try to explain what happened here. This is our first assumption. Then for calculation, we actually change this one to this. Okay, what did we do? Well, we try to absorb these two constants into the eigenvector. So before, your V0 may be something like this. Now you just allow your V0 to carry a constant, which is this. Sounds good? That's the first thing we did. Now with all the former, we actually took this set up. Therefore, all the V0 and V1 we were calculating should already carry those constant. Still okay? Now if you go back and look at our eigenvalues, we did the calculation, we found V1 is 1, 0, but technically V1 should be 1, 0 times any possible constant. Okay, therefore V1 should carry the constant, which is K1, 0. Because it absorbs a random constant into it. Okay, then similarly, when you try to solve for V0, okay, V0 can be anything, A, B. But now, by solving it equals V1, you realize the bottom one has to be K1. That basically means this A can be anything. Still okay? Then we have A. We name this one to be K2, just to stay consistent. So our V1, before we said V1 is this, right? Now we change it. The V1 is going to be this, where K1 is any constant. Your V2, the second part should be the same as K1. This one can be anything, so your V2 should be this. Oh, not V2, V0. Therefore, your final solution will equals this. I know it's a little bit confusing the first time we present it. Is the process clear here? Clear now? Or should we rewrite it again so you can see the clear structure? Do you get it? Good? Okay. So just keep in mind when you try to do the eigenvalues, eigenvectors before, if you end up with eigenvector like this, right? Remember, every time we solve something, we solve the eigenvector is always something like this, but then we say the eigenvector is this. Basically, what we're saying is it's basically a constant times the thing. This constant is basically what we say K1 in general. Okay, so it's just a matter of, do you want to put the arbitrary constant inside or do you want to put it outside? So this will be the solution. Okay, if you write it outside, it's pretty easy to see. Basically, it's this. Where is it? Okay, remember that's what we had for y, and that's what we had for x if we do them separately. All right. So finally, for repeated eigenvalues, we have to settle down y equals this, v0, v1, where v1 come from the eigenvalue, and v0 come from solving this. That will be the whole package for this. Okay. That's it. That's all possible cases for 2x2 system. Okay. What will be the face portrait? Okay. Think about it. You still have a straight line solution, but only one. On this straight line solution, because you have lambda equals -2 on y0, right? Everything goes back. Other than that, you do not have another straight line. Therefore, everything will just be like this. They want to go here, they want to cross it, but they could never cross. So the moment they touch it, they got sucked in. Maybe they come from this way, sucked in. Okay. Maybe they come from this way. Once they touch it, they're sucked in. So you will have something like that. Which we better show by drawing the graph. -2, 1, 0, -2. You have two eigenvalues. Eigenvector is going to be 1, 0. Draw it. This will be the 1, 0 straight line, which is still a straight line solution. You go there, you become a sink in this direction. Everything else got sucked in. But there's no other straight line, only this one. Okay. So back to the beginning, we have this, we have that. Distinct real, complex, lambda equal to 0, finally repeated real. Let's just say this. Now this table is complete. That's all. Oh no. That's all we have learned in chapter 3. Okay. Take a look. Do you have any question regarding any of the cases? All right. Okay. We have 2 more sections left. Actually, 3 more. Let me check. 2 more, 3 more, but basically 2 more. Okay. There will be nothing new, but just wrap up everything we have learned so far and re-explain some leftovers from before. So we will quickly go through it. The first one is general second order linear equations. Okay. We've done this in chapter 2, actually. Okay. This comes from the damped harmonic oscillator. Okay. Now we have a new way. Y prime equals V. Y prime prime equals V prime. Therefore, this is the old setup. This is the new setup. And they are equivalent. Again, it's linear, constant coefficient. With homogeneous. Okay. How do we solve this before? Let's take an example and compare. Now let's revisit. We make a guess. We guess the solution look like this. Okay. Then we go ahead. That's the old way. Okay. Now, new way. So instead of making a guess or anything, we just go ahead and find the eigenvalue. Notice we solve this for the eigenvalue. Before, if we make a lucky guess, we solve this for the whatever lucky guess we have. Can you see the lucky guess actually come from your eigenvalue assumption? So you can basically forget about it. You will always have the same polynomial, so you always have the same answer. Additional step is just try to find V. Okay, B equals negative 2a. This implies V1 this is the first eigenvector. Wow. This is the second vector. So final solution. Hmm? Hmm. which if you check, which will give you the same answer. Okay. But if you solve the one dimension, you only get this one, not the V. For this one, you get both of them at the same time. Andrew?
Is it just by chance that the v value for the eigenvector is the same value as the eigenvalue?
You mean it's -5?
Yeah, the -5 and the -2.
Very good question. What do you think?
I would like to think so. That'd make things easier.
Do you understand that, let's say if you didn't do things in this way, but you found y, can you go ahead and find v, which is technically y prime? Then you take the derivative, you produce a -2 by taking the derivative of this and the -5 for this, right? Okay, so your observation is great. Number one, it's not a coincidence. They happen to be the same. Okay, they will always be the same under the conditions such that the first one is y and the second y is actually v. Good so far? So if you solve a linear system, right, you have x, you have a y. That's a general 2x2 linear system. There's no guarantee your y is going to be your x prime. Sounds good? But for harmonic oscillator, we manually made the second one to be the derivative of the first one. So of course, for this case, we will have it, but only for harmonic oscillators. Does that make sense, Andrew?
Yeah, it does.
Okay, then yeah. So yeah, we got lucky. The reason is because we got this system from this. So we basically say, well, we are going to create a second variable, and that second variable is going to be the derivative of the first variable. But a general 2x2 does not have to come from here. It can be anything. Okay, so in general, this won't be true. But if you get it from harmonic oscillator, it's gonna be true. Good. It comes from the derivative of y prime. All right. So from now on, before we kind of don't feel good because we made a guess. And then we automatically have a question. If you have a quadratic, can you have complex value, repeated eigenvalue, repeated solution and things like that? We have a lot of questions to ask, right? Because you guessed. This time we don't guess anymore. And whichever case you have, we do have a corresponding solution. No matter it's distinct real, repeated real, degenerate, or complex. We all have possible explanations. Okay. That's all we have for this revisiting the second order linear equation. Do we want to do any examples? Well, I don't think so. Let's just write down some common thing. Number one. Okay. This will be a second order differential equation. If we create a variable which is given by y prime, we can transform it into a first order system. Okay, which looks like this. Okay. We call them 1, we call them 2. For 1, We solve it by lucky guess. We end up solving this. And the answer is e to the SD. For 2, we solve it by eigenvalue. Okay, which equals 0. So if assume a does not equal to 0, you multiply on both sides. You end up solving this for eigenvalue. Now we can say firmly, it's not just a lucky guess. They exactly share the same format. So we're not just being lucky there. They always match each other. Okay, so the S you're solving here is basically the lambda you're solving here. We will go over number 3 next time. Basically, we just take all the harmonic oscillator, classify them into different cases: damped, undamped, overdamped, underdamped, critical damped. Okay. But now I want to leave you something to think about. That is, what about third order? It's very possible you can change it to be a first order ODE system. But instead of 2 by 2, you have a 3 by 3. Okay, if you have higher order, you just add one more variable and make one more dimension of your ODE system. So it's always transferable if it's linear. Now you need to go ahead and think about, how do you solve a 3 by 3 ODE system? Will it be similar? Will it be totally different? Okay, we will not touch that in this class, but you should really think about it, because if you recall what you learned in linear algebra, finding eigenvalues, finding eigenvectors, they have no restriction on how many dimensions you have. You can do it for 5 by 5, you can do it for 10 by 10, or even 100 by 100, right? With that in mind, can you think of how you should do a 5 by 5 or 3 by 3? How many different cases can you have? You are going to have 3 real eigenvalues. You have 3 eigenvalues who repeat for 3 times, or maybe one of them repeating for twice, or you have 3 distinct. Some of them are positive, some of them are negative, and maybe you have several zeros too. Moreover, you can have real and complex at the same time. Okay, think about it. And if you have questions, you want to talk more about it, bring it to class. But technically, it's not covered by the course content. Okay, but you should think about it.